to that. So, last lecture we saw how to go about identifying the U1 gauge field in some sense, and I sort of left with something saying that you look at trace of the non-abelian guys. Best to write it in a slightly different way. Forget the trace. Let's write it as f mu nu a and phi hat of a. So, this where phi hat I just normalized it to become 1, phi hat of a, this should be the field strength for the abelian gauge field, and it had two pieces. One was this, okay. So, there are factors which I will not write, but hopefully it's a non-trivial exercise to check that you do get the mu. Let me put indices later. So, let me write alpha and beta times okay. So, this is precisely what we had in the, this is what we expected from for it to be. So, this is what appeared in the topological chart. So, it kind of shows that you can really replace this guy with this guy, okay, because this will not contribute by definition, but it also shows that the fluctuations are abelian. Okay. So, let us get back to the original problem which we were looking at. We had a Hamiltonian density whose energy was this is what we had. If you so I threw away, we were looking at time independent configurations, and with our boundary conditions the various terms dropped out and we just left with these three terms. And the interesting thing is about the Prasad-Sommerfeld limit effectively said that the PS limit said that you says forget about u of I or take lambda to 0, but remember that we need to impose phi a should be equal to mu square upon lambda. Are there any questions? Okay. Is this correct? This is what we had. These were the conditions. So, where u of phi was a potential which we defined long ago. So, basically in the PS limit it corresponds to saying that you forget about this guy. Okay. So, what we are going to do now is try to look at assume that the PS limit is taken. Yeah.
So, writing this is lower, won't it negative sign?
So here when I am that is a good question. Here all these things are all there is only I and j which are space indices, which I will raise and lower now with delta I j Kronecker delta. There are no signs, everything is positive definite out here. That is why I did not even, if you notice I did not write upper ij or lower, I wrote everything as lower ij. Okay. So, that it is a sum of positive terms, I mean, okay. And this pi I of a is, I could have written it this way, it is just a covariant derivative, but this is the notation of Prasad and Sommerfeld. Okay. So, I am just I told you that I wanted to stick to that, and so in notation I am more or less following whatever they did. Okay. So, now let us look at something like this and try to understand. So, this is the energy density that we are looking at, and we will see why B, the name B is added goes with this. We are going to look at energy density which does not have this thing. So, to look at that thing, what I will do is consider the following quantity pi I a plus or minus half epsilon I j k f j k of a mod square. So, by this I mean just taking summing over all A, taking the square of it and summing over all A, this quantity is greater than or equal to 0. Okay. This is not yet this, but we will expand it and we will see, we will get two terms which are exactly this. Okay. So, of course, if this is true, its integral over all space would also be greater than or equal to 0. Okay. So, let us expand it and what do we get? We get, so let us look at half of this. So, we get one term which would be half, half okay, that is just this term. Then the square of this will, if you massage it around, the epsilons will go away, giving you 2 deltas, that will give you a factor of 2, etc., and it will give you exactly this term. Okay. But now you get 2 extra terms, rather the cross term which is plus or minus half YIA epsilon ijk fjk of A. Okay. So, this is greater than or equal to 0. So, all I have done here is to expand that thing. Okay. So, now we can see that these two terms are precisely what appear here. Okay. So, I can rewrite, so this implies that the energy E, which is defined to be integral d cubed of x times, I will just, because I do not want to rewrite this again, I will just call it f plus pi square, okay, maybe even at least let me put this much, the factors, correct. That would be the integral of this should be greater than or equal to minus or plus okay. So, we see that the energy density is okay. So, since this thing is minus or plus, it the strongest one would come when you take the one which gives the positive sign. So, I will take care of that by just saying that it is greater than or equal to modulus of this. Okay. So, this is a very important. So, we get that the energy is greater than or equal to okay. Now, I will write, instead of writing it as pi I A, I will write it as d I of phi A f j k of A. So, this is what we get. Because I forgot to write it. Thank you. Okay. Yeah, thank you. So, now you can see, now you can ask when question two things to ask is when is the equality or when is the inequality saturated. By that I mean when is so the lowest energy configuration would correspond to E being equal to 0. Okay. So, that now that depends on the sign of what you look at. So, coming back to this, yeah. So, the question is when will it be true? It will depend on which sign plays the dominant role. So, it will be one of these two things being equal to 0. Okay. So, the answer is pi I A plus or minus half epsilon I j k, let us write it as 2 terms and determine when epsilon I j k f j k of A equal to 0, or okay. In some sense this is similar to, this parallels what happened in the case of vortices, except now the only thing we need to check, is this the topological charge, and the answer is yes, it is. And the easy way to understand that is to look so let us first look at that and then come back to this. So these two possibilities would have happened. So yeah, so let us look at this. So what would this be? This I can rewrite as this is a covariant derivative of this thing. So also the Bianchi identity tells you that di of f I j k epsilon whatever should be 0. So I can rewrite this. Okay, so the claim, let me write it as a claim, integral d cubed x epsilon I j k should be di of phi I a f I j rather f j k of A is proportional to the topological charge q, and I need something which will give the dimensions of this thing, that is the web of this thing. So it will be mu by root lambda. Okay. So basically the way to see this is that I can pull this derivative out and I can convert, this is a volume integral in 3 dimensions, and we can convert this into just ordinary derivative okay. And then this so now this will become an integral over this this is the total derivative, and it is a surface integral now at the sphere at infinity, okay. And then we can just follow through this identification which we had, and it will show us that what we are getting there indeed is the charge, okay. So this phi a I have to just take it to the other side. So you basically you need to get those two derivatives, and it's just you can work out the details, and so you can see that indeed this is what is happening q, so it depends on the topological charge and mu over root lambda, okay. And there are some factors which I am not going to work out, that is for you to fix, but what this shows is that this quantity on this side is just depends on the topological charge. This is kind of nice. What it tells you is that if you are in the vacuum configuration, that we know is a situation with topological charge 0. In that situation the energy we know is bounded is the from below by 0, and q being 0 there is no contradiction. So yeah.
Why do you apply to the total energy and not to the Hamilton intensity?
Okay. So no, in principle I mean it the thing here is that when the equality is saturated it happens point by point everywhere, but now the charge I need to integrate over all. I mean what I am interested in is the energy or the mass of this monopole or whatever that is.
When I am taking the saturation case,
yeah.
So I can as well do the analysis. I mean
so then no, that's not quite how do I say this, that is not true, right, because the thing is that what you want is the
why would that not, why is that not
no wait, what is your question, repeat, I don't get.
Saturating the total energy, right?
Yeah.
So you get E greater than equal to whatever mod of
Yeah,
the
yeah,
thing.
okay.
But suppose I decided to do the same thing with Hamilton intensity.
Yeah, no, in fact I am doing that, right. I mean the equation of motion I am writing is not for is out here, it is a sum of squares Okay. So, if it something is 0, even an integral is a sum, infinite sum, so it has to hold point by point. So, I mean in fact that is what I am doing, otherwise I would have written a much weaker constraint or something like that, but here this holds point to point. So, it is really one is working with the Hamiltonian density, but I am looking at the energy when I want to get the if you want to get the relationship between the energy and the charge, okay, this is what you get. Okay. So, the good point, the point here is that you are solving first order equations. Okay. So, let us look at this thing. I still need to fix which goes where. So, I just wanted to write out the charge. So, let us look at what happened when we took this to this plus sign came to the other side as minus sign. Okay. So, the modulus is works when q, so this should hold when this becomes positive. So, this holds when q is less than 0 and this holds when q is greater than 0, unless there is a things have been very nasty to me and there is a minus sign in this thing. So, I have to, so let us assume that this is our definition of q, then this holds. Okay. But now comes the neat thing that these are first order equations, because this is pi I is nothing but di of phi a okay, and these are first order equations. Okay. So, this trick is due to Bogomolny, okay, and the Prasad-Sommerfeld solution which we looked at the explicit solution in the PS limit is actually solves the PS solution solves this first order okay. This is an exercise for you, this is just a claim, but it is very easy to go and check, go back and plug it into these two things and check which one it works, for which it works. And of course, if you look at the Prasad-Sommerfeld paper, they do give the mass, and so the mass according to them, or we already wrote this long ago, it was really mu by root lambda, went as mu by root lambda. There were some e's etc., but it is really mu by root lambda, which we have already seen. Okay. So, this is the mass. So, this is exactly like the King solution which we saw, this energy will be really concentrated in some core region and it will fall off, it will go to 0. So, the asymptotic things do not contribute. So, really this again, but this is the point about solving these first order equations is that the mass is determined by the charge. Okay. So, in other words, if you tell me that it had monopole charge 2, you can tell me that and it saturates this equation, okay, then you are done. Okay. So, but I do not think Prasad and Sommerfeld realized that their solutions, of course, whatever satisfies this equation will satisfy the second order differential equation, but the converse need not be true, because obviously there exist solutions for which E is greater than this number with this charge, and they will not have to, at least in principle it exists. Okay. So, this so that is why these two ideas, idea of taking getting rid of the potential is due to Prasad and Sommerfeld, and this squaring trick is due to Bogomolny, and it sort of fits together. Okay. And so today we call it BPS limits. So, when you hear of people talk of BPS black holes etc., these are exactly situations where the charges of the black holes determine their masses. It goes through it is a little bit more complicated setting, but it is really at the end of the day the trick is similar to this. Okay. And so what you find is that it is exactly goes so if you give me the charge, I can give you the mass for these things. Okay. It is real fun exercise for you to go back and check that the Prasad-Sommerfeld solution which we wrote out a while ago actually satisfies one of these first order equations. Okay. So now the point here is to ask, are there more general solutions? There can be dionic solutions, for instance things which carry electric and magnetic charge. Okay, I will show you a beautiful trick which will let you take this solution that you know for the monopole and construct a solution which carries both electric and magnetic charge. Okay. So let us see how that works, and that requires some tricks. So we will work in the PS limit. Okay, this we will keep. So that means at the end of the day it means ignore u of phi. Okay, but if you want magnetic charge, if you want electric charge, implies that we cannot say that A0A is 0. We will still keep everything time independent. Okay, things remain. Okay. So let us look at, first thing is in this sort of a situation, first let us look at what happened to f mu nu a, f mu nu a. Okay. So originally when things were when a0 was 0 etc., we just said that this is equal to minus f I j a, f I j a. Now let me pull everything down, because I have taken care of the sign. This is what we would have got. Okay. But now this term this has a, now we cannot do that because a0 is no longer 0. Okay. So but now we will get an extra piece. So to look at that thing, let us consider the following thing. Let us look at f 0 I of a. Okay. So yeah, let us write this out. So there will be one part which would be d0 ai minus di a0 of a. So first thing to note is that this term dies down. Okay. But what about the other pieces? So then we will get plus epsilon, is there an e, I do not know. Okay, e a0 okay. So all I have done here is to go ahead and get rid of this time derivative, but the rest remains. But if you look carefully, this is nothing but the this I can rewrite as minus di of a0 of a. Okay. So now you can see, now I can write out what I get here. It is just, there will be a 2 coming because it could be 0 I this thing. So I get d2 d0 of ai whole square. Sorry, di of a0, thank you. Okay. So now let us just look at what that does. So now let me just go back and okay, I could look at the Lagrangian or I could look at the Hamiltonian density. Let us look at the Lagrangian density. So the Lagrangian density for such, no, let me stick to the Hamiltonian density. So the Hamiltonian density will look like the following: half I keep writing the wrong one, right, di of A0 okay. I have thrown out this thing. Okay. I do not know if this is good news or bad news. Look at this, there is a minus sign out here, you lose positive definiteness, but there is something interesting which happens. What you see out here is that A0A is exactly, but for this sign, is behaving exactly like phi 0A. Okay. So in other words, I can think of A0A as a scalar with kinetic energy of wrong sign. But in a sense this is expected, because this has to do with the signature of the metric in some sense. Okay, that is where it came from. So just looking at this, we can see that there is a symmetry of the following kind. Okay, so we are not looking at the most general configurations, we have all these conditions put in. So but in that limit things look rather interesting. There is a way I can think of a boost symmetry which is an SO11 kind of symmetry which rotates these two guys. Note both of them are adjoint in the same representation, that is very important. Okay, so I can write something like this. Okay. So it does not act on the A index, it sort of rotates these guys. Okay. So what this tells you is that in some sense, if you think of this as some kind of boost in some sense, you can boost this thing. So you take the other solution of the monopole solution and just do this boost. Okay, at least at the level of solving things, it will give you a solution to the equation. And in fact, if you look at the ansatz which was written out for a dyon, that is something which carries both electric and magnetic charge, it was exactly of this kind. So we already seen so this is what we had chosen for as an ansatz for A and phi when we solved for this thing. So all one does is to add a new variable, h of okay. Have I exchanged J and H? Yeah. Okay. And if you look at the equations of motion, we what we get is something, it reflects. So you can see that what is the thing which is invariant combination under these boosts? It is, yeah. but that will translate into h square minus j square as your invariant. So, we will see for instance in the equation of motion for k double prime we had written something like this, k into k square minus 1 okay, plus k into h square is what we had. Okay. Now, without any calculation we can write the answer what this should look like. It should be just minus what is it, j square, is it. Okay. So, this identification tells you what to write there, because this left hand side and these two terms are invariant under this boost, it does not act on the on this part. So, it goes through. Okay. And now we can write the rest of the equation. So, r square so, this is what we would have got in the precise Sommerfeld limit, plus there would be another term which we had written, but that is the potential in the PS limit, that term is dropped. Okay. So, now again it is very easy to write what the equation would be for j. It would be wherever we see h we write j. And that is indeed the case. Okay. Okay. So, the most so the key point here is now we can actually take the monopole solution and do a boost on it. Now, that will obviously mix these things and it will create something which has electric charge also. Okay. So, boosting okay, what was that solution? That was k equal to C r by sine hyperbolic C r, and it was obviously j equal to 0, h equal to so 2 lectures ago we had written out this thing. At that time we did not have a j, okay, and so now if we just boost it, k will remain the same, and so all we have to do is to multiply this with some cosine hyperbolic gamma, and this should be the same object C r cot hyperbolic of C r minus 1. Okay, and I am just looking at their paper, it agrees with this thing. Okay, so the point is that you get this part for free by noticing this symmetry. Okay, it's a somewhat of an accidental symmetry, it's not a real. Okay. So now you can ask what are why. So this solution obviously will have non-zero electric and magnetic charge. Okay, so the electric charge turns out to be Q electric four pi over E sine hyperbolic of gamma. So, if you switch off gamma, okay, so and the monopole charge will be whatever you had before multiplied by cos hyperbolic of gamma. Okay. So, clearly we can, so this tells you, and you can see that the finiteness of energy etc., nothing actually gets messed up, but you can work out what the Okay. So now the thing is, so clearly it looks like that there are solutions with ionic charge. Okay. So now you can ask what happens to Dirac quantization in the presence of objects which carry dyons. Actually I think this is not correct. The Hamiltonian density is positive definite. It was positive definite when we started. When we wrote it was sum of squares. I think this is positive, but the Lagrangian will have the wrong. Okay, so this is still true, symmetry of the Lagrangian. I was a little bothered by this, yeah. In the Lagrangian that will hold. Okay, yeah. Because if you remember, it just became E square plus B square, even if you had if you take the abelian case. So this is not quite so the Hamiltonian density is not an invariant, but the Lagrangian is. Okay, so I withdraw what I said, and anyway these equations are determined precisely by that. So okay, so this statement is correct, but my statement that it comes from I wanted this expression, so I just I initially wanted to write the Lagrangian density and then I wrote the Hamiltonian. That was my error, but this is positive definite. Okay, so the mass actually turns out to be the earlier mass times cos hyperbolic square of gamma. Okay, it is not so when I came to write the mass, I realized that I was off, and because this would tell you that the mass should also be invariant, but it is not, and the trick also will not, I mean the Bogomolny trick is not quite, you have to do some variant of that. Okay, so now the thing is, suppose we have two dyons of charges, let us just say write it E1 G1 and E2 G2. Okay. So we are trying to write recall that what we had was Eg, if you had pure electrically charged object, and this thing G, this was equal to 2n pi, was it, in natural units? It was quantized. Okay. So now that we just need to find a replacement, I will not prove what it should be, but we should find a replacement for this, which should reduce to this in this case. So I will just write the formula. So the Dirac quantization for dyons takes something like E1 G2 minus E2 G1 equal to 2n pi. Okay. So now you can see what happens is, so let us take a case where G1 is 0 and E2 is 0, then this just becomes E1 G2 is equal to 2n pi, this term drops out. Okay. But if you go the other way around, again this works out, but there is a minus sign, but all that matters is really it is an integer. So again there is it goes through, but more general would be when you have objects which are both dionic. Okay. So this is a formula, I will not derive this thing at all. Okay. But you can convince yourself that at least in these sort of things, that suppose we started out with something where we had E in one solution with E, one with electric charge and this thing, and you write a boost, carry out this boost, can you write something which will work out, and you will see that that will work out provided using the simple identity, this minus sign is important because cos hyperbolic square minus sin hyperbolic square of gamma should be equal to 1. Okay. So this is just a consistency check of what I am saying. Okay. So in some sense what I have in mind is I take with something which is a pure monopole and make it into a dion with a boost. Obviously the same thing, if you give me a thing which is pure electric under the boost, even that will pick up a magnetic field. So now that is an example of a dyon, but we know that that should in the, so this better reduce to that, okay, and that happens. Okay. So is this clear? Okay. So we will come back to this this picture of let us look at the same setup, where one thing we saw is that there was a parallel between this A0 out here and this guy phi A. They were almost on par with each other, because we just said we are looking at these kind of solutions. Now that also gives us an idea that maybe there was the funny signature had to do with A0 coming from the time-like thing, but this came with the correct signature. Suppose I think I took my thing, I had a theory in 3+1 dimensions, but instead of that, suppose I looked at an example of in 4+1 dimensions. Okay. So let us call the 4. So what I am saying here is, we started out with A0, which was a component of the gauge field, and since we are looking at time independent configurations, this was behaving like a scalar, adjoint scalar for time independent configurations. Okay. I could do the same thing. This could have come from some another 4th dimension, where I required that things be independent of that 4th dimension, then I could get something like this. Okay. So that is what I am saying. Let us start in 4+1 dimensions. Okay. And so let's call the 5th dimension I should call it A4, right, A4. So X4 rather, and the gauge field. So I would start out with a gauge field which would have been A0A, then 3-dimensional guys, plus there would be A4 of A. Okay. So now again, as we did here, I will say that look for configurations what would be the analog of time independent in this case? X4 independent. Okay. So again we will do what we did there. We can look at something like F4 of mu. Okay. And this will start looking like d mu of A4. Exactly like we did before, and if I just went ahead and rename A4A as phi A. Okay. Then what would you see? You would see no difference between what we wrote. Once we took the PS limit, that had the potential energy dropped out. So that is all that remained. Okay. So this idea of starting with some 4+1 dimensional object and then doing requiring things to be independent of some dimension. We have done 2 examples today, one is time and the other one is X4. Okay. And this will give you give you a normal scalar, it will not give you funny sign scalars, things will be perfectly fine. So it is called dimensional reduction. And can you guess what one would call the process of going from this thing in the opposite direction? What would you call? You haven't done chemistry? Oxidation. It's called dimensional oxidation. Okay. So the process of adding a dimension in some sense, okay, is called dimensional oxidation. So what we are going to do in the next few minutes is to ask, suppose life was so bad that we had 9 dimensions, space dimensions, and one this thing. Okay. We can go ahead and do this same thing. I can do dimensional reduction. I will assume that so we will take coordinates x mu and let us call the rest y1, y2 up to y6. So this is our normal space time coordinates, okay, and we will choose 6 such guys, and again look at configurations that are independent of y. Let us call this combined things, we will call it y capital A. Okay. The reason to do that is because we will see that there is more structure in this thing, and so out here we just saw that f4 mu became this way, but now we have to look at several possibilities. So we start out, we will have f mu nu A, which is the usual thing, but then I can have one of them to be mu, the other to be A, and so this will look like d nu of some scalars. There will be so many of those things, I will just relabel them and call them phi a's, and they will all carry this gauge index. It is important to note that I cannot oxidize. If this scalar was in some other representation, I could not have done oxidation, because gauge fields in the reduction always give you adjoint valued objects, because gauge fields cannot come in some other representation. So it is important that things be in the adjoint. Okay. So you can see that I get 6 scalars, okay, but this we are not done. There is some more things, which is f a b of A. Okay, and this term will look like f a b c. So you can see, I mean, I am not even specifying the gauge group, I am just saying just take some field strength for some gauge field, okay, some non abelian gauge field. So I have f a b c times okay. So they come with a potential. It is better to think in matrix terms. If you think of this as a matrix, this is nothing but phi phi. Okay. So it is a commutator. So if you look at f mu nu square, this will become the usual f mu nu square. This will be the kinetic energy. Sorry, this will be the usual kinetic energy for the 4-dimensional gauge field. You will get a nice kinetic energy for the 6 scalar fields. You also get a potential for these scalar fields. Okay. Now the potential will be square of this quantity, of course. Okay. So you get a nice quartic potential naturally in this theory. Okay. And so you get a system which has all these things, and you can ask what is the analog of the Prasad-Sommerfeld limit. The analog of the Prasad-Sommerfeld limit will be that phi a and phi b will commute with each other. So you look for field configurations where phi a and phi b commute with each other. In fact, even out here you can see that even here we could have looked at something like f0 of phi a. We had looked at time independent configurations, but if we just for a moment kept that together, you would have seen that there will be one term which will look like a0 commutator phi a. There should have been that term. Okay. If I but they will have to commute with each other, and in our solution they did commute. Okay. So this actually does happen. There is a theory like this, and it is called this theory, if you add supersymmetry, is a theory which is called n equal to 4 supersymmetric Yang-Mills. Okay. And I am giving you the bosonic spectrum of it. It has one non-abelian gauge field and 6 scalars, very easy to see. In fact, these theories, if you want to construct them as supersymmetric theories directly in 4 dimensions, it is very hard. So, Shirk and Schwarz actually constructed them directly in 10 dimensions, where things were easier, and then did a dimensional reduction. Okay. So, this idea of dimensional reduction is very powerful and very useful, okay. And we will come back to this again. We will see how the Bogomolny equations are actually a special case of something called self dual Yang-Mills, okay. And that is what we are going to do next.